Mr. T here. This packet 15 focuses on acids and bases, part 1. In this packet, we're going to go ahead and learn about terminology of acids and bases, which you'll have to memorize. Other terminology includes autoionization, and then very specific definitions of what an acid base is. We'll then get into pH chemistry and convert very large concentration units into very small one called P notation. So for pH and something called pOH. So we'll get into that. We'll then learn a little bit about something called Le Chatelier's principle and ionization constant. Warning, the very first thing that you need to do is learn how to use your calculator when it comes to using logs for pH and pOH. Every calculator is from a manufacturer which likes to do things their own way. So you have to do a Google search for your specific calculator brand, and then you should find a video that allows you to that explains log and anti-log for use in pH chemistry. For example, I'm using a TI-30X. So then I would type in how do you calculate pH on a TI-30X, and then you will find a help video which explains how to use the buttons for that specific calculator. Again, every calculator is different, so there's a different way of doing things depending on what calculator you have. After you learn it, you need to master it. So you'll be doing log calculations and anti-log calculations relating to pH on the next quiz, the quiz after that, the exam, and the final. After we learn about Le Chatelier's principle, then we'll get into some other pH-related concepts such as ionization constant. But let's go ahead and jump right into it. So I'm going to go ahead and start the animation. Well, I'll go through some slides first and then get into the animations just so you can visualize what's happening. The first thing we need to talk about is autoionization. So make sure you're able to memorize this and apply it. So let's first break down what autoionization is. To use an analogy, every society has a bunch of people in it. And in the society, there'll always be a couple bad apples, so to speak, where one person will go ahead and mug and take something from another person, which we call thieves. Well, in chemistry land, water molecules are no different. Here we have a beaker of water, and most of the water molecules are just doing their own thing, floating around, saying hi. But there is a small portion of water molecules such that one molecule will go ahead and steal the hydrogen from another molecule. This process is called autoionization. So now I'm going to go ahead and erase this. And I'll show you your final two products. You have one molecule which has the extra hydrogen. We call it a hydronium, which you already memorized from the polyatomic ion list. The next one we call a hydroxide. That's the one with the missing hydrogen arm. So this occurs naturally inside neutral water. And we've purposely taken out any other ions that are present, which we call deionized water, which means no ions. And it always produces this hydronium and hydroxide. You need to memorize the autoionization equation. So you'll have two water molecules, and then one of them will steal the hydrogen from the other one, forming a hydronium, and then you'll have the disfigured hydroxide left over with the missing hydrogen arm. I know, tragic. Now, this occurs very, very, very little. So if I were to sit there and have 1 liter of water, then these acts of stealing occur for every 0.0000001 mole of water. Now, it's really hard to keep track of all the zeros, so we like to use scientific notation. So 1 times 10 to the negative 7 moles of H2O. So, assuming we have 1 liter of H2O, which I'll label on the beaker, then you will have 1 times 10 to the negative 7 moles of H2O, and you have another one that's 1 times 10 to the negative 7 moles of H2O. And after the reaction, you will now have 1 times 10 to the negative 7 moles of, and I'll use my purple pen, H3O plus that's present, and then moles of the OH minus that are going to be present. Now, we like to use solution concentration units. So rather than say that due to autoionization we naturally have 1.07 times 10, 1 times 10 to the negative 7 moles of hydronium, we'll like to go ahead and use molarity. So this is moles divided by liters, and then here we have 1 times 10 to the negative 7 moles of hydronium. And then we also have 1 times 10 to the negative 7 moles of hydroxide divided by 1 liter, and then this gives us 1 times 10 to the negative 7 molarity. Now, I did make a little mistake there, so let me go ahead and clean this up a bit. I'm going to get rid of that moles that you see right there, and I'm going to add in my capital M for molarity, or M underline, which implies to be moles per liter. So I'll do the same thing on the bottom. So 1 times 10 to the negative 7 molarity of hydroxide. So this occurs naturally in neutral deionized water all on its own. And nature always has a balance. 1 times 10 to the negative 7 hydronium and hydroxide. Now, we do get lazy after a while. Instead of writing out H3O plus, we'll often do this. It will be summarized as this notation, H plus, and that means H3O plus. We get even lazier, and instead of writing it like this with molarity, we'll go ahead and we'll put brackets around it. The brackets indicate molarity. We just didn't write the symbol for molarity on there. So brackets indicate molarity. So in the bottom one, I could go ahead and erase the M. and then I can go ahead and put the brackets. Now let's go back to the original slide. Here is the autoionization equation showing one molecule stealing hydrogen from the other one. There's the hydronium. Here is the autoionization equation that you need to memorize. We talked about the large concentrations. Usually we write it in scientific notation, and we like to use brackets. And all of this is occurring in water, so it's implied to be aqueous. Now, we need a way of artificially increasing or decreasing the amount of hydroniums. Same thing, we also need a way of increasing or decreasing the amount of hydroxides. Because it turns out that some reactions occur better than others if there's a high amount of hydroniums floating around, or a high amount of hydroxides floating around. We can automatically assume that if we start off with 1 times 10 to the negative 7 molarity of hydronium and 1 times 10 to the negative 7 molarity of hydroxide, we can assume that this is going to be a neutral water. Ergo, if we go ahead and add in an acid or a base, then we can go ahead and change the neutrality and increase the amount of, again, hydroniums, or decrease it. So these special substances we call acids and bases that change the number of hydroniums and hydroxides, and we say that we make the solution acidic or basic. Now, we have different definitions. Some of the definitions in a working definition, they kind of overlap with each other. Other definitions, there's clear differences. But you need to memorize these definitions. The first one is Arrhenius definition. That's and so we call this an Arrhenius acid, and it's any substance that produces hydroniums when put into an aqueous solution. So it's put into water. And then bases are any substance that produces hydroxides when put into water. So for example, here I have neutral water. I go ahead and I put in an acid such as hydrochloric acid, and the minute I put it in, it produces the hydroniums. So there's H+, and then I have something called a spectator ion that just kind of floats around. Now, as a reminder, what's actually happening is the hydrogen is actually inserted onto a water molecule, forming a hydronium and a chloride ion. But we just simplify it as H+. Conversely, if I were to sit there and have a base such as sodium hydroxide, that's going to be added into the solution along with a spectator ion. So we're increasing the amount of hydroxides if we were to sit there and put that in there. Let's go ahead and see some videos giving an overview of acids and bases. So in this video, here's an example of hydrochloric acid. The white portion of it in the model down below is a hydrogen. The green portion is a chlorine. It's considered an acid because it increases the amount of hydrogen ions according to the Arrhenius definition. So there's being put in water. They separate, or what we call ionize, forming a hydrogen ion. And it's implied that that's actually H3O+. Now, we talked about electrolytes last time, and electrolytes, such as a strong electrolyte, excuse me, let me go back, such as a strong electrolyte, it completely dissociates. It completely turns into ions. So this type of acid is also known as a strong acid because every single HCl separates into the hydrogen ions and chloride ions. We also have other type of acids. So this is nitric acid. Notice how it completely dissociated, so that's also a strong acid, aka a strong electrolyte. This is a weak acid, aka a weak electrolyte, because it doesn't always separate, and when it does, the original molecule could want it back. Here are examples of strong bases, meaning all of the bases we put in, they're strong electrolytes, they completely separate, such as sodium hydroxide, potassium hydroxide, calcium hydroxide. And they completely dissociate into their counter ion metals, such as sodium, potassium, and the hydroxides. So the silver portion, that's the metal, such as sodium and sodium hydroxide. And then the red and white portion, that's a hydroxide. Because we've increased the amount of hydroxides in the solution, due to us adding a base, we call it basic. That's a basic solution. So, strong base, strong electrolyte. Now there's different types of bases. This is a very popular one, even though it doesn't have that same metal and hydroxide look to it. This is ammonia, NH3, and that also acts as a base. It acts as a base by creating a hydroxide rather than dropping one off and producing one because it already had one. So it does this by stealing a hydrogen from another water molecule, similar to the autoionization process, and you'll notice it created a brand new hydroxide. This is considered a weak electrolyte, ergo a weak base, because it doesn't, not all ammonias will take off a hydrogen, only some will, and as soon as it picks off a hydrogen, it may give it back. So see how it gives it back. And it changes its mind and it picks it up, forming a hydroxide, and then it gives it back. We still have a basic solution. Now that we've seen examples of acids and bases, let's really go into these definitions. So an Arrhenius acid is any substance that produces hydroniums, and it summarizes H+. So, and if we have HCl and it's going to be put in water, we don't call it hydrogen chloride, we call it by a special name hydrochloric acid. And the formula is written like this, where we put AQ on it, because it's going to be dissolved in water. And then a Arrhenius base is any substance that produces hydroxide. And here is an example right here, sodium hydroxide. And we have to write it with AQ for aqueous because it's going to be put inside water. Now, we have alternate definitions of acids and bases. The big one you have to memorize, or the other one you have to memorize, is the Bronsted and Lowry definitions. They define acids as any acids that donate hydrogen. Memorize that. And then any bases that accept hydrogen. Now, practical purposes, there is no real practical difference between Bronsted and Lowry acids and Arrhenius acids. They pretty much function the same. So here I have a Bronsted and Lowry acid, hydrochloric acid, and it donates a hydrogen. Now, Bronsted and Lowry bases, this is a little bit weird, but we define it as anything that accepts a hydrogen. So this is going to be a bit redundant, but on slide 5, here is the sodium hydroxide. When I put it inside water, the hydroxide comes off, and it fits the definition of Bronsted and Lowry base because it picks off a hydrogen from a nearby water molecule. It then produces a new hydroxide, which is extremely redundant, since there's already one there that was present, but that's okay. And then a brand new water molecule. So sodium hydroxide fits both the Arrhenius base definition, as it donates hydroxides, and the Bronsted-Lowry, in that it accepts hydrogens from water molecules, forming new hydroxides. So why do we have such a definition? Well, the main culprit is ammonia. So even though there are no hydroxides present, so it cannot fit the Arrhenius base definition, it will pick off a hydrogen from water, as seen in the video, and form an ammonium. Yummy. In the process, it generates a brand new hydroxide, making it a basic solution. So make sure you have those definitions down, especially the example related to ammonia, since we'll see that one. So let's see a summary of these definitions in action. I've donated I've dropped in hydrochloric acid into water, so it produces hydroniums, so that satisfies the Arrhenius definition. I've also donated the hydrogen, aka hydronium itself, and that completes the Bronsted-Lowry definition. We've increased the hydroxides for a base, so that fits the Arrhenius base definition. And we have that redundant reaction where the hydroxides picked off the hydrogen from other water molecules, forming the brand new hydroxides. So that fits the Bronsted-Lowry. Although really it's the ammonia that we apply the Bronsted-Lowry reaction with. Alright, so make sure you know those definitions, have those memorized. Now we need a way of dealing with very large numbers and making them really, really small. So let's go ahead and show you this slide first. We need a way of quantifying the amount of hydroniums and hydroxides in a solution. Because there's a nice relationship between hydrogens and hydroxides based on the Le Chatelier's principle, which we'll get into a little bit later, all we have to do is just focus on one component. In this case, the standard in science and industry and the health field is to focus on hydroniums. And what we like to do is we like to take the concentration of hydroniums, because they tend to be really big numbers, and make them small numbers, which we call pH values. Now, the P notation is a math term which means negative log. So we're going to take the negative log of our hydronium concentration, and it's going to be in molarity. As a reminder, I had the original H3O plus molarity, but we got lazy and we used brackets and a single H plus to describe the same exact thing. So P notation means negative log, and then you have brackets which mean molarity, and H plus means hydronium. So here we have a very acidic solution. This is 1 molarity of our hydrogen ions. So 1 times 10 to the 0. And then down here, we have a very dilute hydrogen ions. So this is, if I were to sit there and draw it out 0, 0, 0, 0, I'm going to make a mistake with all those zeros. So I'm just going to have scientific notation right there, 1 times 10 to the negative 14th. It's a really, really small hydrogen ion concentration, the smallest that we can get. However, it's still a big number to mess around with, so it's just much easier to turn it into a pH value. So we're going to use something called negative log on our calculator, and we're going to put in the molarity, which happens to be 1 times 10 to the negative 14th. When we do that, we will have a nice, easy, simple value such as pH equals 14. Let's go back. Hydronium ions, they're the total amount of hydrogen ions, and it's in molarity. There's going to be a range from 1 times 10 to the negative 1, although we could technically go to 0, but we tend to stick with negative 1. That's going to be 0.1 to 1 times 10 to the negative 14. I apologize, it should be over here. And if I turn this into decimal form, it would be a nightmare accounting for all those zeros. Maybe that's it. Using P notation, which is negative log of the molarity for hydrogen ion concentration, we can turn it into pH values. Now, I need you to be aware that the lower the pH value, the higher the concentration. It's inverse. So as I decrease in pH, I increase in hydrogen ion concentration. So a low pH tends to have a very concentrated amount of hydrogen ions, and we say it's extremely acidic. Whereas a high pH tends to have a low concentration and it's basic. So it has that inverse relationship. So over here, highly concentrated, low pH value of 1, such as stomach acid. High pH value, that means it has a low concentration. And you'll see this nice inverse relationship again between hydroniums, or H pluses, and hydroxides. So the more concentrated the hydroniums, the less concentration of hydroxides. And we'll explain that concept a little bit later on. We then have these nice crude cutoffs, kind of like what we did with polarity and nonpolarity, where if you have a pH that's less than 7, 0 to 7, we consider it an acidic solution after adding in the acid. And if it's greater than 7, it's going to be a basic solution, usually because we added in bases. And then if it's directly at 7, then it's going to be a neutral solution. We didn't add a acid or base to it. So it naturally ionizes, say that 10 times, naturally auto-ionizes, producing pure Di water. Di means no ions until we actually have auto-ionization occurring, and then you have the 1 times 10 to the negative 7th hydroniums and hydroxides that are going to be present. That's a lot, so let's go ahead and give you some relative terms. If you have a pH of 1 or 2, that pH 1 is a stomach acid. Usually if we're dealing with chemical reactions, we need to have smaller pHs. So we could have a pH of 0.1, or we could have a negative pH. So a pH of like negative 6, for example. And that's when you start getting into more concentrated, like 5, 6 molarity acid. pH of 5, that's rainwater. So rainwater is actually acidic. And then when you have a pH of 9, then it's considered more of a basic solution. That means there's so little hydrogens that it's mostly hydroxides. So baking soda, and then pH of 14, super little amounts of hydroniums. It's pretty much all hydroxides. So Drano, or pure sodium hydroxide, fits into that category. So make sure you know the relationships, molarity and pH. You can also do taste tests. Wouldn't do it with Drano, that would be awkward. But if something is bitter, such as baking soda, it's going to be basic. If something is sour, then it's going to be vinegar. Such as vinegar, then it's going to be acidic. So if you drink a soda, for example, that tends to be highly acidic, so it has a sour taste. You can also use another type of qualitative test, such as a litmus paper. So for example, red litmus paper that turns blue, that's going to be a basic solution. So here are more examples. You can go through those. Now let's get into the pH value. Now, there's some shortcuts. I want to teach you the first shortcut, going backwards in time. Here's the first shortcut right here. We can automatically assume that if the coefficient is equal to 1, then whatever that exponent is, that exponent value is going to be the pH. Pretty simple trick. So if I have 1 times 10 to the negative 7 for my molarity of hydrogen ions, then the pH is going to be equal to 7. If I were to sit there and change this to a pH, or a 1 times 10 to the negative 3, then the pH is going to be 3. So I like that little trick because you don't have to do any calculations on your calculator. Now the hard part, if you were to sit there and change this value to something other than 1, then you have to use your calculator. So for example, let's say I have a number like hydronium is equal to 2.67 times 10 to the negative 3 molarity. Then using my calculator, and I'm doing this in real time, I'm going to go ahead and have a pH of 2.573. So that little exponent trick doesn't work with any coefficients other than 1. So FYI. Now at the beginning of this commentary, I talked about going to the internet and learning how to use your log and anti-log on your calculator. You absolutely need that on the upcoming remaining quizzes and exams. So this is what we do. You're going to go ahead and in parentheses or brackets or however your calculator works, you'll put in the molarity if we want to know the pH. You'll take the negative log of it. And that's going to equal 3. I should point out that as soon as you create, as soon as you have a log value right here of 0.001 or 1 times 10 negative 2 that you put in there, you will have a negative answer here, a negative 3.0. So you need to multiply it by times negative 1, so that way you have a positive value, because pH values are always reported as positive values, unless they're super concentrated, but I'm not going to do that to you. So the pH of vinegar is going to be 3.0. Now, let's say, so if I were to have another example, let's say I have a hydronium concentration, or hydrogen concentration, hydronium, hydrogen, tomato, tomato, same thing, of 0.025. I then go ahead and put that into my calculator. The negative log of 0.025. And I'll do this in real time. So negative log, and that's going to give me a pH, whoops, my bad, a pH of 1.60. Now for the bad news. Sig figs. Sig fig rules are weird. I just can't express this enough. They're just super weird. Just accept this is how it is and move on with it. So if we're going from hydrogen concentration to pH, you're going to have to count the sig figs. In this case, there's going to be 2 sig figs. And then the sig figs is equal to the number of decimal places on your calculator. Weird, huh? So, in this case, I counted the 2 sig figs. So it's going to be 1, 2. And then that's going to be equal to the number of decimal places. So in this case, on my calculator, I rounded it to 2 decimal places, 1.60. So that's how you account for proper sig figs, going from hydronium to pH. Now we're going to do the opposite. We're going to go ahead and give you the pH, and you're going to be asked to find the hydrogen concentration, aka a hydronium concentration. Here is the formula for it. We have to use something called the anti-log. Anti-log. And this is where different calculator manufacturers have their own preferences. Some of them will have this 10x function on your calculator. Other ones will say something like a log. So it's your responsibility to go to Google, and there will be a video out there for that specific calculator to figure out how to properly perform anti-log functions on your calculator. So, but assuming you know how to do that, you're going to go ahead and use the negative value. So in this case, 10, -6. By the way, there's going to be a plus or minus function. So if you're looking at the video for how to use your calculator, they'll mention this, and you have to use that. Please do not use the traditional minus, like where it says on the corner of your calculator, times, divide, plus, minus. That's a different symbol, and you'll get a wrong answer. So it has to be the plus minus symbol. So it's going to be 10 to the minus 6.0. And then this gives you the molarity, 0.000001 molarity. Now let's go through the rules, and I think there's a mistake in this one, so I'll have to fix this. No, there isn't. I take that back. So for sig figs, we're gonna go from decimal places of our pH value to sig figs of the molarity. So for example, using the example that we have already created, there is only one decimal place value, the 0, in the milk example. Therefore, there should be only one sig fig present in your conventional as well as scientific notation coefficient. So that's a bit tricky, I know. Let's do another one. I could start off giving you a pH of 8.976, and then using the anti-log function of a negative pH, you are going to get 1.06 times 10 to the negative 9. Now let's go through the sig figs. There are 3 decimal places. Therefore, there needs to be 3 sig figs in your molarity concentration. Bottom line is, I'll be giving you questions like this right here. And you are going to have to apply the proper formula. So you have to have these memorized. So in this case, I'm going from molarity to pH. So pH of 3.0, pH of 2.0. Notice these have a coefficient of 1 for these examples, so then I could just use a little cheat method. So this is 1 times 10 to the negative 3, so there's the 3. 1 times 10 to the negative 2, there's the 2. And then for the other ones, I need to find the molarity from the pH. And notice if it's a complete whole number with nothing but zeros for trailing zeros, then or has nothing but trailing zeros, then I can kind of do the reverse cheat method and just put 1.0 times 10 to the negative 4 times negative 2. Realistically, I'm going to give you a combination of these as well as ones that you have to calculate out. Especially because I spent so much time on the calculator, I'm still going to give you ones that are like this on the bottom, where you have to calculate those out. So what is the pH of a solution that has a hydronium concentration of 0.0845? That's pH of 1.073. Now I'm going to try to trick you. This is HCl, and you might not have noticed this, but we've automatically assumed that it's going to separate and form a single hydrogen ion, or hydronium when it combines with water, and a chloride. We call these monoprotic acids. Now this next question is super easy. If I'm dealing with the molarity of HCl, then the concentration of hydronium ion is going to be the same answer. So it's going to be H plus, or hydronium is going to be 0.902 molarity. Now really I only need brackets around the 0.902 if I'm describing molarity. So I'll go ahead and I'll erase the brackets around the H plus. If you did it, you'd still be the correct answer. So I know that's a bit weird, but it's the same value, 0.902. That's the molarity of the hydrogen ions. Alright, let's move on. We're now going to go ahead and go straight to POH. The calculations are identical. You're not really learning anything new. The health and industry standard is to look at pH, but it is possible to look at the POH. Very easy, especially when you're adding in strong bases. So let's go ahead and go through this quickly. Here I have a 0.010 molarity of sodium hydroxide using the Arrhenius definition. It creates one single hydroxide. So whatever the molarity is of the sodium hydroxide, it's going to be the same thing as hydroxide concentration. So I'm just going to go ahead and do this. Hydroxide is going to be 0.010. Whoops, I don't need that molarity thing there. Let me erase that really quick. Just put the brackets, because brackets mean molarity. Now, I need to go ahead and turn that into, I need to go ahead and turn that into POH. So, very easy. Use the same negative log that we used for pH, 0.010. And you can either use the shortcut if it's a whole, if it's just a 1, excuse me. Let me say that again. If it's a molarity with a value of 1, Then we can go ahead and turn this into scientific notation. And that's 1 times 10 to the negative 2. And because the coefficient is 1, it's a whole value of 1, not 1.5, but just 1, then I can either use the calculator or use the shortcut method, and then this gives me a pOH of 2. Pretty straightforward. Actually, it should be 2.0 in this example that I just made right. 2.00. Oops, my bad. So be sure you're comfortable with these calculations. So what is the hydroxide concentration for pOH of 7.0? We then have to use the antilog. It's the same exact process. So 10 to the negative 7 for antilog, and then that gives you the hydroxide concentration 1 times 10 to the negative 7 molarity. You'll notice we have different ways of writing the same thing, which I'm sure you guys will love. You have plenty of options of how to represent the data. Another way to do it is like this. They both mean the same thing. So practice with these hydroxide and pOH calculations. And again, realistically, I could give you something that looks like this, where I give you a number that is not a whole number of 1, but it's some other value which forces you to use your calculator. So in this instance, I'd have to go ahead and use my, well, that'd be easy. This one actually is a super easy one. Be careful of these. So sodium hydroxides, using the Arrhenius base definition, they always form one single hydroxide. So therefore, for this top one, the hydroxide concentration is going to be equal to the same molarity. That was so tricky that I almost confused myself. So this would be the final answer. I could put you in a situation like this, where, and let me just go straight to an example so you can see what I'm talking about, where I start off giving you an acidic solution, and then you're asked to figure out the pOH. So notice the OH. So we're basically going from an acid concentration unit to a basic concentration unit. Or I could ask you to go from a pH unit to a basic hydroxide concentration unit, and vice versa. Maybe I start off with a pOH and go to a hydronium concentration unit. So let's go backwards in time to figure this stuff out. First thing we need to investigate is something called Le Chatelier's principle. So say that 10 times. Le Chatelier's principle. In short, nature loves a balance. So here is a giant beaker. Let's go back to our neutral solution. So we're going to have neutral solution of. And nature loves a balance. So here we have 5 hydroxides, 5 hydroniums. The hydroxides are on bottom, hydroniums are on top. And everybody's happy. Now we're going to go ahead and be mean, and we're going to add in an Arrhenius acid, such as hydrochloric acid. And I'll go ahead and I'll use my purple pen. So I'll add in 2 extra hydrogens. Now, nature loves a balance. When we upset the balance, then nature tries to reset the balance. So I've upset it by adding in more hydroniums. Because there's more hydroniums than hydroxide, nature is very unhappy about this. So what it will do is it will try to sacrifice some of its hydroxides in order to reset the balance. This is all in vain. It actually shoots the hydroxides in the foot, metaphorically speaking, and we end up with less hydroxides. But this is what nature does. So using our auto-ionization equation in reverse, we know that 2 water molecules, I'm writing in the lower left-hand corner, form my hydronium and hydroxide. So what we're going to do is we're going to go backwards. We're going to sacrifice some of our hydroxides in a vain attempt to reset it. So here, this hydronium and hydroxide will go ahead and form water again. And then this hydronium and hydroxide will form water again. Although we decreased some of the hydrogen ions, we also massively decreased our hydroxides. So it's a bit pointless, but this is what nature tries to do, and it's called the Le Chatelier's principle. So in general, the more acidic you make the solution by adding in more hydrogens, the more sacrifices nature makes with its hydroxides. What we find is as the hydrogen concentration or hydronium concentration increases, the hydroxide concentration decreases. They have an inverse relationship. Conversely, if I were to sit there and add in sodium hydroxide, and increase the amount of hydroxides, and I'll add in a whole bunch, then nature will go the other way. If there's a lot more hydroxides than hydroniums, then nature will sacrifice its hydroniums in order to try to, in vain, try to restate the balance. So we see this for hydroxide concentrations. Getting a little bit messy, so let's go back to our summary. So, based on Le Chatelier's principle, as hydrogen ions increases, hydroxides decreases, or conversely, if you're dealing with a basic solution, as hydroxides increases, hydroniums decrease. And then this graph tries to show you the inverse relationship. So negative 12 for hydroxide, that's really, really small, and then negative 2, that's a lot. So as hydrogen increases, the hydroxide decreases. So there's this teeter-totter effect. The other one's the same way. As hydroxide increases, notice a negative 2. It's a really large concentration. Whereas negative 12, think 0.000000000000001, that's a really small concentration. So the hydrogens decrease. Now, let's apply this to math. Automatically, nature has decided that the product of the hydrogen and hydroxide concentration should always equal 1.0 times 10 to the negative 14th. And this value right here we call the ion product constant. So there's always going to be that relationship. Now, we can do some math calculations based on this relationship. And this follows Le Chatelier's principle, where if I had something like this, I had a 10 to the negative 8 for hydroniums, then automatically I'll have a smaller amount for hydroxides, 10 to the negative 6. But I want us to cut down the math a bit, so what we're going to do is we're going to take the negative log of everything. And when we do, we have this simplified ion product constant formula. So it's pH plus POH equals 14. I need you to go ahead and memorize this. You still need to memorize that this number right here in its molarity form is the ion product constant. But you're going to use this in order to perform the math calculations to interchange between pH and POH. So this is pretty straightforward. If I was given a pH of 6 and I wanted to know what the POH is, then I just have to plug it into this formula right here. So the pH in this case would be 6. Here's our X. So we have 6 plus X equals 14. X is going to equal 8. So therefore the POH is going to be 8. So what is the, let's do an easier one just to start off with. I came up with some examples on the side. Given a POH of 8.9, what is the pH? The pH should be 5.1. We're taking a 14 minus 8.9 based on the ion product constant equation in logarithmic form, or P form. And then given pH of 6.7, then our POH is going to be 7.3. So that's pretty straightforward. Now the harder part. Instead of giving you, for example, the pH, I could give you the molarity. So you're going to have to do a couple calculations. The first thing you'll have to do is convert the molarity into pH. And you'll have to take the negative log of it. 1 times 10 to the negative 1. When you do that, that gives you a pH of 1. And then subtract it from 14, and that gives you a POH of 13. I could ask you to go one step further. So in this case, I start off with a pH of 4.00 of hydrochloride solution. Because it's monoprotic, it's only going to give off one hydrogen, then that's pretty straightforward. It's just going to be pH of 4. I need to go ahead and subtract this from 14. That gives us a 10. And now I need to turn the POH into hydroxides, in which case I use the negative log and then 1.0 times 10 to the negative 10 molarity. Or excuse me, it's hydroxides, and the it's going to be anti-log, and that's going to be 10 to the negative 10.00, which gives us the molarity that you see there. So you want to go ahead and practice with these problems. I could give you tougher ones, such as the one you see down here. And you're going to have to go from, that's a little bit more challenging. You're going to have to go from hydroxide to POH to pH to hydrogen ion concentration. Because the coefficient is not a whole number of 1, then you're going to have to use your calculator. So here's the answers. I had to go from hydroxide to POH, which is 11.60, to pH 2.40, and using the ion product constant equation in P notation, or P form. And then once we have pH of 2.40, then I use the antilog negative in order to turn it into molarity, which is 4.0 times 10 to the negative 3 as the final answer for what is the concentration of hydronium ion in solution given, the hydroxide 2.5 times 10 to the negative 12. I also did the problem below it for what is the pH of a solution that is a hydroxide, 0.853. And going through the same format, I only need to go up to pH this time. So the final pH is going to be 13.931. So be sure to practice these. Also take advantage of any pH tutorials or calculators that your instructor wants you to practice with, so you can master doing these techniques with your calculator. Now, my final comment is it's highly recommended that you memorize this table that you see here. Let me go ahead and drop my highlighter. This table that you see right here that I'm highlighting in yellow. This shows you the big picture as you practice these problems over and over and over again. So for example, if I'm starting with pH and I need to go to POH, then there's that ion product constant formula to go from pH to POH. Again, it's 14 is equal to pH plus POH. And they have arrows showing you how you can manipulate the formula to get your desired results. If I wanted to go from pH to hydronium, then I'd have to go ahead and use the antilog that you see here to get to hydronium. If I want to go from hydronium to pH, then I have to use negative log. Same thing with POH. Going up, I have to use the antilog to get to hydroxides, and then use the POH or negative log in order to go back to POH. That's a mouthful. So highly recommend that you practice writing those formulas on a scratch paper so you can take advantage of that on a future quiz or exam, or just master it so that way you can use it automatically. People tend to do really good on this portion if they practice using their calculator constantly, so that way they can avoid any calculator mistakes. And this concludes our acid bases part 1. Thank you.